Alright, this is our senior project, the bridge tester for ELM 4702, project part 2. This is Ben Holloran, I'm Carter Mealy.
So what we're going to talk about is the background of our project, the course, the things that led up to it, the course, how we decided to fix the problem, the solution that we had to the problem, our system diagrams, how we hooked everything up and designed everything, and areas of responsibility, estimated timeline, a quick budget, and then the conclusion.
Alright, our project background, we were to design and build a piece of testing equipment for public stick bridges specifically designed for the Trotsky Bridge competition. We also want to make the project open source so that anyone else can go into the project. Our budget was given us about $3,500, and our sponsors were John Diebold and Gordon Reynolds from the Civil Department. The actual Trotsky competition is held at Concordia University in Montreal. Multiple colleges from international schools compete to build the strongest possible stick bridge. The strongest bridge currently was made by MIT that held over 3 tons of force. There's a tiny load display, as you can see on theirs. This is a bridge after it has been crushed. And there's this piston up here with a piston extender because it doesn't have all much throw in the world.
So I did a little research on the current tester that they have. In 1984, they had a tester built by a bunch of students like us. It worked pretty good. They held competitions. In 1991 was their first competition that they actually opened up to U.S. teams. And I haven't been able to verify this, but I think that Vermont Tech was the first team to actually compete at Concordia. In 1994, a kid built a really strong bridge and was in the middle of testing it when the tester exploded. The piston, part of the piston flew off, put a giant mark in the ceiling, which is still there today, and it covered the entire audience and all the judges with oil. So they decided to get a new crusher. The new crusher had a maximum force of 6,000 pounds and was built for the end of the year. They were never actually able to find out how much that kid's bridge held, so he got a special award. The new crusher that was built in 2000 has uses a hydraulic jack, and then there was another one built in 2010 that also uses a hydraulic jack, which is seen in the picture up there.
Alright, our design specifications. Our design is basically governed by the rules of Trotsky competition. You had to build it around the bridges themselves. So the bridge has to span exactly 1 meter. Our tester has to be able to output at least 10 tons of force. We decided to make it mobile enough to move between buildings easily, fit through doorways. We want to have a large load display, unlike the current tester, so that our load display could be seen from the back of a very large room. The current one only has a display of about 1 inch tall, ours has 4 inch tall numbers. We want to be accurate within 1% of the maximum load, and we want to be precise to within 1% of every load. Our piston is a 14-inch throw piston, so that we can have many bridges of different heights and still only have to use 1 piston.
So the final design that we came up with, we were looking at different ways of putting force on a bridge. So one way you could do is you could put a giant weight, get a tank full of water, and fill it with amounts of water. The amount of water you put in there is weight. We were thinking about using a piston on the bottom to pull it down. There are other ways of providing force in a hydraulic piston, but it turns out a hydraulic piston is basically the easiest way to do it and the cheapest and most robust. So also, instead of using an I-beam like the current Trotsky competition, we decided to use a truss. 2 reasons: it's lighter and it deflects less. And also, we didn't know, we were looking at I-beams for price. It turns out a truss is a little more expensive, but that's still good. We also decided to use a Raspberry Pi. We originally thought we were going to have to use an Arduino or some micro to control all the different electronics and sensors. But then we thought that with a display we were going to also need a computer. A Raspberry Pi gives us the ability to have I2C, which is a micro type communications network, and have an HDMI port to run a 22-inch monitor. So we're going to use I2C, which is something like Serial, but it can control many devices at once. On the I2C is going to be the 4-inch 7-segment displays, and the deflection data, which is how far the bridge is bent as it's being crushed, and the load data, which is how much force the bridge is taking at that moment. So, our system diagram, here's how it all lays out. First, we're going to have, well, the most important part is that there's a hydraulic piston that's going to crush the bridge. We also have a truss on the bottom and a truss on top to take all the force. And then there's a giant 7-segment display so that people can see it. This will be our LCD screen, which will allow the technician who's running it to save the data from the different poles. It will also display the curve of the bridge, that the bridge came up this far and then broke, this one came up that far and broke, that one came up that far and broke. It will be force over deflection and will give us interesting data, which is a bit more data than the current Concordia tester can provide. There will be a control box on the side where we can, well, the Raspberry Pi will be held and some buttons and all the things that are needed to run it. And the main bread and butter of the construction is 3 by 3 inch by 8 inch wall, hollow steel tubing. We found out that 8-inch thick steel was fine for the loads that we were going to see. On the bottom, we're going to mount all the hydraulic stuff. That will keep the center of gravity down so it won't be tippy. And we'll have to run the pressure lines up to the piston, but that will be fine. So, the way that we're going to do the hydraulics, we're going to use, basically, it's an electrical splitter. There will be an electric pump running a gear pump, or electric motor running a gear pump, which will provide pressure, which will then get fed into a wood splitter style valve, which has, you pull it down and the piston will come down, but you can lock it up to have the piston retract while you can go do something else. And when it hits the top, the valve will pop down. There's a pressure release valve in place, which will allow the, which will make sure that the piston never has more than a certain amount of pressure on it, to make sure we never break the frame or doesn't damage anything. There'll be a tank to store the hydraulic fluid and a filter. Make sure we don't run goo and stuff through the pump. Another interesting thing is we're going to put the hydraulic pressure sensor as close to the piston as possible to cut down on the fluctuations in pressure produced by the pump. The colors over here also show the different sizes of pipe thread that are needed for hydraulics to help the order of the right lines.
All right, this is the frame. It's a fairly basic design. We have a 3-part truss on the bottom. We have a 3 by 6 by 3/8 inch hollow square tubing main beam. There's a piece of aluminum gets mounted right under here. This is what takes the brunt of the force. And then these trusses here, they distribute force nicely. Here at the feet, they just barely fit through a standard doorway as we were planning. We also have mounted very large casters in a lot of them for very easy roll and movement. These are the main structural supports on the side. They're also 3 by 3 inch hollow square tubing. Then we have this truss over here with a cradle that holds the piston, which is mounted up in this hole right here, slides down and hangs right in the middle there. These upper trusses also absorb a lot of the force. What we did is we did a SolidWorks force analysis of our design. We did without the top beam on. The top beam is virtually a 0 force number. Here's the actual model that we did our system on. And here it is after the simulation. It looks like it deformed a lot, but that is actually, I believe it was 600 times the actual deformation, so that a human being can actually see how far it was deformed in relation to the other parts. We found out that the factor safety is about 4, which means that our design is about 4 times stronger than it needs to be.
You can see the force concentrations are here and here. We did actually test the top truss of the beam separately, but this one was much clearer to understand what was going on. So here's the I2C. This is one of the modules that is going to run the LED 7 segments. So we've got a display about this big, and we need 5 of them because we need 220. We need to be able to display 20,000 pounds. So that's 5 digits, and they're all exactly the same. The way that I2C works is you just give each device that's on the bus a different address, and you can address them separately and feed them data. So we found a chip that will control the 7 segments. We're using resistors for current leveling, just simple We're going to build 5 of them, and we're going to give them at unique addresses, as I said. The 2 serial lines for I2C are an address line or data line and a clock line. This chip needed 3.3 volt power, but the 7-segment display needs 12 volt power, so there's a bit of we need multiple power supplies to do that. But it's fairly simple. This chip that we were actually using did not actually work the way that we planned on it, so we had to swap to a different chip, but it's basically the same, it just doesn't have all these extra things.
All right, here is the bracket that connects our electric motor to our hydraulic gear pump. This is a custom fabricated ring that sits and bolts very nicely to the base of the electric motor. 4 of these holes are for the motor itself. The other 4 are for these large aluminum standoffs that allow us to have the distance we need while still bracketing the gear pump to the motor. In here is a Lovejoy coupler, which is basically a coupler that allows a little bit of flex while it's spinning. And on the top here is the bracket that the gear pump actually attaches to. Gear pump holes over these holes, and these holes bolt to the bracket, which then just fits here very nicely. No problem. These little gaps allow it to only have a few points of contact, which means it stays more level. It's more stable that way.
So this is the blueprint of the motor face pump, or the bracket, the ring that we was talking about. I did some GD&Ts. We wanted basically wanted these holes to be within 10 thousandths, which gives the bolt it ensures that the bolt has 10 thousandths clearance around it in all cases. The center of this plate fits over a ring on the motor face, which will give it, which will align it concentricity. Will give it concentricity, and then these holes will hold it down to the motor, and then these countersunk holes, a bolt will go through it the other direction and bolt it to those 4 standoffs, the 2 standoffs.
All right, our current project status as we sit today, our frame is all welded up. Our piston is mounted on the frame in the cradle in welded position, not going anywhere. Our software is currently being finalized. It is almost finished. We just need to tweak it a little bit to make it play nice with all the other hardware. Our hydraulics, we are currently in the process of mounting them. Our gear pump now has the bracket made. The tank and the piston are both mounted. Once all of our hydraulic bits are in place, we're going to string on the hydraulic lines and they're done. Also, our hydraulic handle is in place as of today. Our frame needs a little more work to be ready to paint. Basically, we just need to get all the electronics attached and all the holes that need to be tapped and drilled, Our load display needs to be assembled. We know it works. We just need to stick them all together and attach them to the frame. And some of our software still needs to be written, but as we said up there, it's being finalized. We're almost done.
So here's the work breakdown. We used a program called GitHub to do our project management. Another thing it does is, and 2 things it does. One, it puts it on the internet where it'll be open source and other people can see it, and also tracks changes. So every time we make a change to the project, we save that change with a comment so that we can go back and say, oh man, we're just working 5 minutes ago or a month ago. You can go back to that state that it was a month ago, download that, and you'll be able to work again. GitHub is a free hosting website so long as the project you leave on there is free to the world. And when we put all the things together, they gave us this handy-dandy graph. So this shows us that our load display was over the time frame. We were on February 10th, but it was projecting that we weren't going to be able to finish the load display in time. These are all the tasks that we had to do for the load display. Now, Carter has blue tasks and I have green tasks. So Carter is working on the load display, but when we're working on the frame, I had a couple things to do on the frame, but Carter had a bunch of things to do on the frame as well. But it was tasking him to do those after he finished the things on the load display. We didn't follow this 100%, but it kind of broke everything down for us. And the length of this showed us how much work we had to do. And also it showed our project was broken down into the various different parts, sub-assemblies, and showed who was the main person. For example, the force sensor, I was doing all the force sensor, and Carter was doing all the load display, and it broke down nicely.
All right, here is our budget. This also doubled as our bill of materials. everything that we bought, or projected we're going to buy, is on here with associated links. I believe we took the links off for the sake of looking on this particular one, but on the one that we use, we have our hyperlinks, so we can just open it up. We need to look up a data sheet, like let's say we need to look up the 7-segment display data sheet for common current needs. We would just open it up with a hyperlink immediately right there on the website with that particular 7-segment display we're using. As you can see, we've come in under budget so far, just barely. We're at $3,300 roughly out of our $3,900 budget. Materials, raw materials was fairly inexpensive. Steel's fairly cheap. About $300 for raw materials. Mechanical bits like casters and a bunch of hardware that we're going to need, they came in just under $500. Our hydraulics is where it got expensive. That came in at just under $1,700. Hydraulics are very expensive, and our sensor itself, that alone costs $400. It is a very, very precise sensor that can handle up to 3,000 PSI, and that is quite a bit of pressure. That is enough pressure that if the hydraulic line were to rupture, it could cut your finger off with the pressurized fluid. Our electricals came in at $600, which was reasonable. We've had to change a few things along the way, like the 7-segment driver, which didn't work as we thought it was going to. But with that, we have still come in under budget. And in our conclusion, our design meets our client specs and the specs imposed on it by us as well. We are going to be finished within the required time frame before April 25th when we have to present it. And our design is currently within the final budget.
Any questions?